There we go. All right. So this is the new LSM 980 that you have on the in the core facility. And what I want to do is just give you a very quick overview of sort of the modes of imaging that you can do with it, because otherwise this can kind of get lost as we get into the details talking about the hardware and the tech side of things. So the new confocals that we have, the next generation of microscopes, which is what you just brought in, there's a few different key features of them that I think are really quite helpful and prominent. And one of those is the fact that we're working now with diode lasers. So anybody who has been working with the older 880 or some of the older generation systems, you're used to basically letting things warm up a long time. You're used to letting things cool down, waiting to hear fans shut off and things like that. You have a lot of different laser lines available for excitation. So you have the 405 for DAPI, 445 for CFP, something for GFP, YFP, 561 for your reds, 639 for your far reds. These, you still generally want to warm them up a little bit, but there's no cool down period anymore. So that's kind of a nice feature for this system. Another thing is that the entire confocal is powered by Zen Blue, which is going to be quite different than the Zen Black that you've been using on the 880. And some of the older generations confocal systems as well. And so this is very powerful in terms of offering a few different things. One is that it has full camera support. So you do have a camera on the microscope, and we can use this either for navigation or just for very quick imaging. You also have more sophisticated tiling and focus strategies, and it fully integrates in a more advanced way with definite focus 2 as well, which is our cover slip focusing mechanism as well that you have on the system. And then there's a lot of different modules that support things like AI sample finder to help navigate and find your sample, image analysis, and so forth. The 980, just like the 880 does have full spectral imaging. So with the single sweep of all your lasers, you can basically collect all of your signals at once and do unmixing to be able to tease those apart. And you also have on the system Airy Scan 2 as well. And so this is something that the other system had as well. This improves resolution at very high sensitivity, and done the right way, you can improve speed with this acquisition as well. So in terms of resolution, we're talking about a 2-fold improvement in every dimension over confocal, and we're talking about a 4 to 8 times improvement in sensitivity. The 2 behind the Airy Scan means that we have faster processing and reduced file sizes. We'll talk about that more tomorrow. And building on what we developed with Airy Scan Fast on the 880, there's also a new thing called multiplex mode. And multiplex mode basically allows you to take that same sensitivity, still with improved resolution, and give you either a 4 to 8-fold faster acquisition time, whether you're doing confocal resolution or whether you're doing super resolution. And to make this extend better to 3D volumes, you also have a Z piezo on the stage. So the Z controller is a piezo stage. We'll talk about that as we get into the hardware. And you don't necessarily need it all the time, but it vastly improves acquisition speeds for 3D volumes, especially when we start using multiplexing. I'm going to talk about the objectives up front, because often as we're going through hardware, this can be the first thing that I forget to talk about. So just to nip myself in the bud, I guess. I do want to mention that you have a few different air objectives. So you have a 5x. This has a crazy working distance of about 12 millimeters. This is where you really want to start if you're working with a new sample or converting the stage to work with another sample on it. And this is also the one that we're going to use for your sample finder and navigation. There's also a 10x air objective and a 20x air objective. Both of these are beautiful entry-level confocal objectives. The 20x is often used even for things like multiplexing and tiling to get really nice Airy Scan images and really nice confocal images as well. The 25x that you have, this is a multi-immersion lens that has a correction collar that allows you to adapt for water immersion or glycerol silicone oil. And it has a very nice long working distance. That's the LD, 570 microns compared even to the only 500 for the 20x.8 Air objective. And the LCI basically stands for live cell imaging as well. So it's really kind of geared towards that type of application. You have two different oil objectives as well, and those are the 40x 1.3, then the 63 1.4. The 63 1.4 is a Lyra grade, which means, or super resolution grade, which means that it is basically handpicked for the point spread function that it has to make sure that it is compatible very nicely with Airy Scan as well. So again, if you have any questions about these objectives, let me know, but certainly we'll be working with them as we go through also. So I'm sure that we can have additional questions come up as we go. I guess one thing I'd like to mention before we move off of this topic is for the 20x8.8 objective, the Air objective, you notice that it's only a 500 micron working distance, and truly for all of your Air objectives, it's really best if you clean the oil off the bottom of your cover slip if you ever go from oil back to air. But these ones you especially need to be careful of, the 20x and the 10x, because they are close enough to the cover slip that if you leave a drop of oil hanging on it, you will end up cleaning it off. So just please be, for everybody involved, please be very, very careful with those, not to go back to oil. And one of the things that you have on this microscope are a lot of different navigation tools that mean once you collect kind of a Google map of your sample, a low mag image showing where everything is, you shouldn't even need to go back to air anymore. So that's kind of what I'm going to focus on to some extent as we're going through this. Let's talk about the different imaging modes that your microscope has as well. And so really, there are 5 different ways that you can image on this confocal, and the sample prep doesn't really need to change. The applications you're working on don't really need to change. You basically have full flexibility in terms of picking and choosing these as you walk up to the microscope. So one of the things that you can use is the camera. You have an AxioCam 305 on the system. This is good for fast overviews. This works with what we call artificial intelligence sample finder. And I'm going to show you that as we get into working with the software as well. So camera is very nice for a quick overview of your samples. You also, of course, have standard confocal on the system. So we have full control over different detection ranges. We have up to 10 simultaneous detector ranges at once. Not that you'll ever use it, but you can set up the hardware so that you have these specific detection ranges so that we can move very quickly between tracks as we're scanning. And this is what we're going to spend a little time playing around with this afternoon. You also have full spectral imaging, as I mentioned before. And so in a single scan, we can get a full spectrum from your blues to your far reds. And we can use linear unmixing to tease apart up to 10 different channels, including things like autofluorescence, including background, any kind of laser reflection should that ever come up, although it never does. So lots of different ways you can work with spectral imaging to really pack in fluorophores to your samples. And this is something that I've personally been doing for probably 15, 16 years. So I'm too old. And so it's one of my favorite things to talk about. So please, I'm hoping that I can make this feel as comfortable as possible as you look at doing these kinds of multiplex applications. You have Airy Scan as well. And so again, super resolution, twofold improvement in that resolution, high sensitivity, and this is something that you can use when you need to during the course of your sessions. And then we, of course, have multiplex modes. So for things like large 3D volume acquisition, very fast and very sensitive, this is a great way to go as well. The scan head, we're going to show the hardware very quickly, but I just wanted to mention kind of, yep, go right ahead. Is there a question? Okay. So for confocal and for spectral, we're basically going to be using what we call a quasar detector. And so this includes a spectral detector that you see kind of at the end of this rainbow of separation. And then there's a couple of side detectors as well. And then there's a few different prisms and stops in front of it that allow us to send light to these different detectors. So this is how we get those 10 different positions and the spectral type of imaging. The central detector is very sensitive. It's this gasp. And then the two on the side are these metal alkali, sort of the traditional PMTs. We can always come back to this image again if you'd like to, but really they're picked for their spectral sensitivity. And so they work very well across the whole range. You can use this, and there's a different options that we have available, but the one that you have here at the Whitehead is the full spectral, the 32+2. And so what that means, if you take a look over on the right-hand side here, is that we have these two side detectors, as I showed before, and then we have the central gasp array. So this sensitive array can either be used in combination with these different prisms and stops to be able to detect up to 10 or 8 in total different signals, so 10 overall different ranges, or we can just open everything wide up to be able to collect the full spectrum across the gasp array and then do spectral and linear unmixing. And so where this is helpful is in situations where perhaps you have some native fluorescent signals. So in the case of this plant sample, for example, we have a few different fluorescent proteins. We have some chemical stains like mitotractor and FM4. And then we also have the chlorophyll that's sort of inherent in this plant sample as well. And so the idea here is that using two different laser lines, using the 488 and the 561, we're actually able to tease apart 5 different signals from that. And taking that one step further, for samples where people are working with heavy amounts of antibody co-labeling and multiplexing, we can actually work with all of the different lasers that you have available on the system. And even for samples that have quite a high amount of spectral overlap, we can label multiple markers of interest, multiple epitopes, and including things like autofluorescence. And we can basically tease those different signals apart. And so you can see the end result here with only honestly just a few of these fluors showing, because there's enough of them that it's hard to show in a single picture at this point. But we do a very nice job of getting clean separation of multiple fluorophores this way. The other detector that we have is on the scan head at the back. Again, we'll point the camera around and I'll show you what this looks like in a minute, but you also have the Airy Scan module. And so this is responsible for the super resolution and also the multiplexing as well. And very quickly, we'll go into this in more detail tomorrow, but the Airy Scan is basically a hardware solution to provide super res. And we do that by effectively taking a traditional confocal where you would have, for example, the laser coming in, exciting your sample, emission signal comes back, goes through a pinhole where you lose a lot of your light, mostly out of focus light, and collect that signal on a very sensitive PMT. So what we've done instead is we're using basically the Airy Scan to replace the pinhole. And so by doing that, we end up being more sensitive, we collect more light, and we don't throw anything away. What that means is that compared to standard confocal, which you see on the left-hand side right here, where you might set your pinhole to the sort of conventional 1 Airy unit for a good compromise between signal retention and optical sectioning, you'd end up throwing out a lot of your sample information and getting effectively confocal resolution. Even with the regular confocal, if we wanted to, we could close down the pinhole even more. We could throw out, as you see on the bottom here, a lot of the signal coming from the sample, but we would improve our resolution. It's just that signal to noise becomes a serious issue with this. And so the Airy Scan basically combines these two approaches in that it gives you effectively a collection plate that is about 1.25 Airy units in diameter. So we collect more light than we would with confocal, but each one of these individual elements is only 0.2 Airy units in diameter. Let me shake my mouse and get it back. And so we get more signal as a result. We don't throw out light like we would with the pinhole. So basically, once we're done processing, we can retain a lot of the signal that comes from out of focus places, put them back where they belong, and we end up getting improved resolution with better signal as a result, which is the idea of what you're seeing right here. Okay. Again, we'll go through this in more detail tomorrow, but I just wanted to give you a quick introduction to some of this. Multiplexing basically takes this Airy Scan detector and the technology that we built using Airy Scan Fast, and it allows us not to only collect a single pixel at once, but we can actually collect up to 4, or on your microscope, even 8 different pixels at once, because we know spatially where these are located, and we can solve the detector for basically 4 or 8 different pixels at once. And what this means is that we can basically sweep 4 pixels and then at a time in parallel, and save time as a result, and photo bleach less as a result as well. So it's more gentle and it's more sensitive and faster. So this almost gives you a bit of a budget in terms of working with the system. So you can see, for example, that if you have the luxury of time and sensitivity and resolution, you can do things like increase the field of view or do some tiling in the same time it would take you to collect a regular image. You can also go faster as a result as well. And this is even just an example from the 880 days, but just giving you an idea of what you can do in terms of speed. So really push the limits up to, let's say, 100 frames a second or so. And beyond that, if you want to budget that extra speed to be able to do multiple channels, you can do that as well. And so we can add in extra channels if that gives you more information on some of your samples. Alternatively, we can start to look at things like 3D volumes. And so that speed can be kind of used or budgeted to be able to push the kind of imaging that you would normally do with confocal even further this way. And again, no difference in sample prep. So it's just a question of what you want the system to do. So I guess at the end of the day, the point that I'm trying to make is that it's all very flexible.
So there's a question in the chat.
Okay.
So how does multiplexing affect resolution and signal to noise?
Great question. It's right here. So I'm not going to spend a lot of time on this slide. I'm just going to flash it at you, and we can keep it for posterity. Also, you'll have these slides available anyway. But basically, to take a look here, the different multiplexing modes that you have on the 980, you'll see that even when you're doing multiplexing compared to regular confocal imaging, we're still getting an improvement in resolution for each one of these different methods. Confocal 8Y, where we're basically sampling the same way that we would, the same Nyquist sampling that we would do for confocal, you're going to get the same kind of resolution. But for everything else, you're still seeing an improvement, actually. And then the speed you can see down here below as well. Field of view is kind of there also. And the resolution for confocal is kind of dashed out, but basically the idea is that this would be sort of green wavelength light, where you're looking at about 240 nanometers in X and Y and about 700 or 750 in Z. Does that answer the question?
Yeah.
Silence means yes. Great. Okay. So the other thing I want to talk about very quickly is the fact that we're using Zen Blue. And there are, I think, kind of 4 major themes that really are improved with Blue compared to past software. So I just want to quickly cover these before we really dive into them later. And so there is a module that you have, which is called Zen Connect. This is a great way to basically link your images and link your projects together, even across multiple microscopes, so that you can keep a footprint and see where you collected images across a larger field of view or a larger tissue sample, for example. So Connect is very nice. Navigate, you have something called AI Sample Finder, which is going to allow us to quickly focus and identify our regions of interest on the sample. You also have very comprehensive tiling and focus strategies. The system comes with Experiment Designer as well. And so this lets you basically turn the entire Zen into Lego and just custom build different experiments the way that you want. And you also have, for processing downstream, Zen Flow, and Zen File Watcher, which allow you either to batch process or even just at the end of acquisition, chain together a number of different processing steps so that they all happen automatically and you don't need to run through all of those steps manually. The system also has image analysis. And so for regular intensity-based segmentation, also for machine learning, you have those two options on the system. And for these last two things especially, it's worth mentioning that there's an offline PC that is sitting right next to the microscope as well that has a version of Zen available, so that if you want to do these things offline while you or somebody else is still acquiring images, you can do that in parallel with the rest. And one of the places where that really comes in handy is with Airy Scan, where when you're doing the Airy Scan processing at the end, you can just send it to the second computer and have it work in parallel. Zen Connect, I know we've got maybe 2 minutes before we really want to switch gears, but very quickly to flash some images and show you kind of what these look like. Zen Connect basically is, as I mentioned, is going to keep all of your full images and whether they're 3D or overviews in one place. And so you can see an overview kind of in the center of the field. And every image that you collect is basically going to end up going to the same folder so that you can keep track of everything and you know where everything ends up. In terms of tiling, let's see, I might skip through this actually because we don't have a lot of time. We'll do this for real tomorrow anyway. But basically very intuitive tools and ways that you can set up tiles, and you can even use these things for these kind of quick overviews like you see right here. Or we can also use these for things like, setting up support points, and I'm going to skip that. So when you're working with cover slips that are tilted, when you're working with multi-well chambers, when you're working with samples that aren't flat, all of these are cases where things like support points can be very helpful, because what they'll do is allow you basically to deal with the rolls and the contours of your sample. So rather than getting an image like this, which was taken across a flat cover slip, but still 1,300 different images, you can see that without any kind of focus strategy, you basically end up losing focus over time. So all of these cells really should have these very elaborate neurite processes. And if you do this with a kind of support point map, you can see basically what you're missing if you aren't able to work with this. So this allows us, as I mentioned, if your sample looks like bacon, this allows us to follow the contours of your bacon. And you have different ways that you can do this, and this is going to be part of the advanced talk tomorrow as well. So we have support points, which are built into the tiling software. We also have definite focus, which is a cover slip focusing mechanism for every sample except for something using oil immersion with a cover slip with mounting media that matches the refractive index. This works fantastic. So for live cells, for dry objectives, for water immersion, this works great. It does need an RI mismatch to work. And so for microscope slides that are totally RI matched, it's not going to work for those. But otherwise, great way to basically focus on samples over time and over large areas as well. And then you also have software autofocus too. So you can pick a channel and you can basically use that to focus through your sample, find the brightest spot. So as long as your sample does only have one bright spot through the thickness, this is a good alternative as well. If you have a thick sample that has multiple DAPI labeled nuclei, the algorithm is going to pick its favorite, but it might not be your favorite. So you just need to be careful when you want to use that. And your system has full incubation as well. So this has basically temperature, CO2, it has humidity control. It doesn't have oxygen on it, but that could happen if you needed hypoxia. You have a dark enclosure around the system as well, which lets you work in this lighted area. And a lot of different tools to basically try to give you access while you're still keeping everything contained and equilibrated. Everything is fully controlled through Zen as well. So all you need to do is basically activate the channels that you need, activate the incubation components that you need, turn them all on, and you're ready to go. Image analysis, again, this is going to be the topic for another day, but I wanted to just mention very quickly that you have full intensity segmentation and the ability to work with all of this through them at Zen. I don't know if you have other analysis platforms that you're working with, like let's say Halo, Amaris, or, yeah, okay. So you might not need this, but you should at least know that it's here. It's not that what?
It's not bad to have more than one
Yeah,
analysis.
exactly. And this is something, again, with like Flow and FileWatcher, you can actually automate the throughput so that you just end up with results at the end, which is nice. So again, intensity-based segmentation, we can recently do things like zones of influence, where you can basically identify something like a nucleus and look at zones around it. And then you have machine learning as well. So for cases where intensity or your eye aren't really able to tell apart different things, but you know that there are subtle features in terms of frequency and everything else that matter, that identify and set those different components apart, you can use this and build it into your regular image analysis if you want to. Can we use the system to record 3D images in a single frame with high frame rates? For acquisition with multiplexing, that would be the direction I would take that, and yes, you can. You even have things like guided acquisition. So one of the nice things about the analysis built into Zen is that you can actually automate acquisition, basically transitioning from something like a low mag overview to a higher mag, more detailed acquisition if you want to as well. And so the idea of something like guided acquisition would be to do a low mag overview, let's say with a lower mag objective with a single channel or just a couple channels that let you identify the features that you're interested in. Let's say you're looking for dividing cells or something that co-localizes with a couple of different proteins. You can then get the software to do during acquisition, without you being there, an image analysis to identify those features that you're interested in. And then you can go back and do a detailed experiment. Now, the only place where this can trip up is if you need to move to water or oil to do that. But you can basically do a nice final collection with a full panel of different fluorophores in 3D with Airy Scan or whatever you want at the end of that experiment. So this is kind of the ultimate endpoint for some of the analysis that we can do in Zen, I would say. All right. I think that's it. You have lots of people here to support you. I'm not going to bore you with that. But you've met Doug and many of you already, and you've got me. There's a couple of different specialists in the area and tons of service engineers. So lots of attention, I hope. And that's kind of it for the presentation.